This is a shipping problem in which we are shipping oranges and grapefruit in crates with restrictions relative to their volume and weight, and we're going to try and maximize the profit. If we have R crates of oranges and G crates of grapefruit, first of all, by default, we assume both of those are greater than or equal to 0. Since the volume of an orange crate is 4 feet cubed per crate, then for R crates we'd have 4R feet cubed. Similarly, we'd have 40R pounds and $2.50 times R profit contributed by the R crates of oranges. Similarly, for the G crates of grapefruit, we'd have 6G cubic feet, 50G pounds, and 4G dollars profit. I totaled these. The P function is the function we're going to be maximizing, and we'll come back to it later. We have some more constraints to add. G must be less than or equal to R, since the shipper is not permitted to have more crates of grapefruit than oranges. So G must be less than or equal to R. Also, the capacity of the truck limits the volume to 300 cubic feet and the weight to 2,800 pounds. And so the feasible region is R greater than or equal to 0, G greater than or equal to 0, G less than or equal to R. And now I'm going to, instead of writing 4R plus 6G less than or equal to 300, I'm going to isolate the 6G is less than or equal to negative 4R plus 300. And I'm going to isolate the 50G so that it is less than or equal to negative 40R plus 2,800. Then I'm going to solve each of these inequalities for G to get G less than or equal to negative 2/3 R plus 50. And in the second case, G less than or equal to negative 4/5 R plus 56. The reason I did that is to show you that in constraints 4 and 5, as well as 3, we get G less than or equal to a function of R. So we're going to be looking underneath the lines. We want to find the points that are on or under all three of those boundary conditions and in the first quadrant or the adjacent axes. I want to go back here and rewrite the constraints here in a single line for the volume and the weight, because I think that makes it easiest for us to find some ordered pairs to plot our lines. So we're going to look for ordered pairs in the form R comma G. And I'll let you confirm that when R is 0 in the volume constraint, that G will be 50. And when G is 0, R will be 75. And for the weight, when R is 0, G will be 56. And when G is 0, R will be 70. Take time to look at that if you need to. So now I'm going to start by graphing G equals R. Here is G equals R. Remember that we're looking for points that are below this line. So I used the red pen for constraint number 3. Let me change the color to blue and use that for constraint number 4 here. First of all, we're going to use R as the horizontal and G as the vertical axis here. And so for constraint number 4, that's our blue constraint here, that's this one here, we want to find 0, 50 and 75, 0. Drawing that line will give me this. And for this, the 5th constraint, I will use the green. So we want 56 on the G-axis and 70 on the R-axis. So as I draw it, I'm coming down there. So the area that is below the red line and the blue line and the green line is this area here. This is the area we're looking for. One of the vertices is 0, 0. We also have an R vertex here and a Q vertex here. And so we will proceed to find the R and the Q vertices so that we will be able to list all 4 vertices and find the maximum profit. So going back, I will copy down that the profit is 2.5R plus 4G. But we need to now find the coordinates of R and of G. So looking at R, we see it is at the intersection of the blue and red, which is constraint 3 and 4. Those boundary conditions are G equals R and G equals negative 2/3 R plus 50. Since G equals R, I'm going to substitute R for G in the second equation, and that is 3/3 R. So if I add the negative 2/3 R, that'll be 5/3 R equals 50, and that gives us that R equals 30. And so if R equals 30, G is also going to equal 30, and so we have the ordered pair 30, 30. For Q is at the intersection of constraint 4 and 5, where the boundaries are can both be given in terms of G equals, and so I set the right-hand side of those two equations equal to each other. And get that 6 equals, and now I'm going to take the coefficients of r and raise them to 15ths. So this is negative 10 15th plus 12 15th r. That is 2 15th r equals 6. So r equals 15 over 2 times 6, which gives 45. I'm going to back substitute that into the equation G equals negative 4/5 r plus 56, and get the 5's to cancel. So negative 36 plus 56 is equal to 20. So 45, 20. And so we now can find which of these provides the maximum profit. Certainly 0, 0 provides no profit. 30 times 2.5 plus 4 times 30 gives us $195 for the R vertex, and 45 times 2.5 plus 20 times 4 gives $192.50. And 70 times 2.5 gives $175. So the maximum appears to occur at 30/30, and so in order to maximize the profit, we would have 30 crates of oranges and 30 crates of grapefruit. And that would be our answer.